mind what I did there. That's nothing. That does not concern any of you. This is a normal lesson. All right. No. All right. No. Stay where you are. Stop. Stay where you are. Okay. So today we are going to finish off talking about how this polarity affects substances. And so this is kind of a little bit of a look into why we have a theory on bonding. And essentially the reason we have a theory on bonding is to try to explain what we see in the world around us in terms of substances. All right? So around us we are surrounded by all kinds of different substances, and they all have different states, physical states. Solids like the desktop and the walls and the floor, liquids like water and various other liquids. Here we got soap that's in the liquid form, et cetera, whatever you see in the liquid state. And then obviously gases surround us. The air is a gas. We try to compress gases into tires so that tires are nice and round so we can roll down the road. So essentially, when we as chemists or scientists propose this theory of bonding, we want it to be able to explain what we see around us, all right? And that's what we're going to talk about today. How does this whole idea of bonding, ionic and molecular, how does it kind of go together with what we see in the universe and around us? And the title to this one is called Intramolecular Forces and Intermolecular Forces. And in actual fact, we've already talked about one of these types of forces. We've already talked about the intramolecular forces, and I'll describe and explain to you how we've already learned about this. And so today's lesson is actually technically on the intermolecular forces. So let's first talk about what is meant by these things. So first, go back. First, let's define intramolecular forces. So there's the definition there. And we already know intramolecular forces. In actual fact, the whole unit up to this point has been on intramolecular forces. So the intramolecular forces are the attractive forces between atoms or ions within the compound itself. These are the things that hold the compound together. And as I've stated, we've already talked about this. Ionic bonds, opposite charges of ions that holds them together. Covalent bonds, whether it's polar or nonpolar, the single and double and triple bonds that we've been talking about are the bonds that are within the compound. They're inside of it. Intra means within. So all of the stuff that we've talked about in this unit up to this point are intramolecular forces. They hold the molecule together. What we want to talk about today in more detail is an intermolecular force. So intermolecular forces are attractive forces between adjacent molecules. So again, a big difference between what we're talking about right now compared to what we talked about in previous classes is in previous classes, we've only dealt with one molecule at a time. We drew a Lewis diagram for, say, a water molecule or perhaps for carbon dioxide, and we only looked at it as an individual molecule. What we're doing now is we're asking what happens when we put a whole group of those molecules together. What do they do? So instead of just one water molecule, we're talking about a container full of water molecules, a beaker full of water. So how do those water molecules interact with each other? Or carbon dioxide. Instead of just one carbon dioxide molecule, we're talking about what if we had a tank full of carbon dioxide? What would those carbon dioxide molecules do with each other? All right, how would they interact with each other? The answer to that is the forces between them. What is happening when you bring those two molecules together? Is there an attractive force? These intermolecular forces are what is responsible for physical states such as melting point and boiling point and other good stuff that we see. It's what determines why something is solid at room temperature, like the desktop, and why something is a gas at room temperature, like the air around us. The stronger the intermolecular forces, the stronger the attraction between the molecules, and the more likely that it's going to exist in a condensed state. A condensed state is either liquid or a solid. So the particles within this desktop, they have very strong intermolecular forces. And so if I try to push my fist through the desktop, I don't succeed because those molecules are holding on to each other so tightly that they don't get out of the way, or I can't break that force that's holding them together. However, if I'm in a swimming pool and I'm trying to run through the water, I can push my body through the water, but it takes some effort, right? We've all played like tag or something, or, in the water. You know what it's like to move through the water, right? You kind of push the water out of the way, you kind of lumber through the water, and that's because there's some weaker forces holding onto them, and in order to get through, you've got to break those forces so the water can go around you. In terms of a gas, the intermolecular forces between all of the particles within the air is very weak. So it's easy to walk through the air. It moves around us quite easily. We can still feel the effect of the moving air. A little breeze comes past our skin, but it's very easy to walk through the air because the intermolecular forces are weak. So the stronger those forces affects what physical state it exists in and how we can interact with that. Now, just to kind of give us an idea on what we mean by inter and how that means between. The prefix inter, again, means between. And it's probably used in a couple of places. Let's say you wanted to drive to Florida for March break, and you're going to take a particular road, and the road you likely take is something called the interstate, right? You've ever been on a trip where you've gone down the interstate, all right? You probably take I-75 down to Florida. Interstate simply means a highway that goes between states. It links the states together from one state to the next, all right? So inter, again, means between. Another place that you might have heard of the term inter is the internet. Have we heard of the internet? Yes, you've heard of the internet. All right. There was some anniversary, I think, because it was funny. They were playing on the radio interviews about, that was in 94 or 93 when it was just kind of firing up. These people on the radio host, could you explain this internet to me? It was really quite entertaining. So what is the internet? It is a connection between computer networks. So we have our computer network here at school, and if you want to communicate with another computer network somewhere else, you use your internet browser. Use whatever one you want to use. I like to use Chrome, and you can connect to other networks. Just one second. We can also talk about an intranet. At school here, we have an intranet. It is the school's network. So we can actually access various spots within our network. So we all use Google Classroom now, so that uses the internet. We're going to use Google servers. But in the past, we used to use the H drive. Remember the good old H drive of a couple of years ago? Does anybody still use the H drive? Did you remember using it, though, maybe in grade 9? Anybody? You have to use the H drive on the computer system? You did that, maybe? So that H drive is a storage device that is in our school. It's in one of those rooms back there full of computer kind of equipment, and it's within the building. So that network is our intranet, within our own network. If you want to use Google, you then have to use the internet because you're going to use their network. Okay, so intra means within, and inter means between. You got a question or a statement? What do you got? Okay, all right. See how I did that? I just kept ignoring you. So I don't want you to draw this one. This is water molecules being kind of linked together. I'm going to draw a simpler example. So let me draw an example that's going to represent what I want you to represent. So let's start by drawing an HCl like we were drawing yesterday so often. HCl, okay? Left, because I'm going to draw another HCl on the right. And we already know that the delta En for this is about, I think, 0.96, if I recall from yesterday, which means it's polar. And we can represent that dipole, again, just as a review, as an arrow with a little plus. Or I could represent it as that slightly negative and slightly positive. Both ways work just fine. And that's one molecule by itself. And if I were then to label this, oh, and I wish I had a better color, I'm going to just put a label arrow right there. And I know it's really hard to see the blue. I'm labeling the line in between, and that line is the intramolecular bond. This is the intramolecular bond. All right? Within. If I draw a second HCl, now I'm going to talk about how two HCl's interact together. I'm going to line it up like this. And the reason I'm going to line it up like that is because when you bring more than one of these HCl's together, when we bring them as a group, the positive end, the H end of one HCl will be attracted to the negative end of a neighboring HCl. So there will be a weak force of attraction, and I'd like to change my color here. Let's see if I can change the color. I've tried this once. Let's see if I can change that color. Let's change it to a light color like that. Okay? And so there will be an interaction, and I'm going to draw that as a dashed line, in between the negative end of one and the positive end of the other. And that particular interaction, and I know I'm going to be going back to yellow, that particular action is the inter, the in-between. Okay? And because they have opposite charges, there will be an attraction there. And that's what we're talking about today. What happens when you bring a bunch of molecules together and how they're attracting to each other. Okay? So we've defined intra, within, single bonds, double bonds, triple bonds, good old regular bonds we've talked about. We've now defined inter, in between. And so let's now take a closer look at these inter, in between ones, and let's name them and classify them. All right. The first type is ion-ion forces. And I've got a picture there, and it's kind of a three-dimensional structure to show you that that overlapping structure is three-dimensional. Remember at the beginning we talked about this lattice structure. I'm going to draw it on the board here, and you can draw this, and we've done this before, so I'm only going to make it kind of smallish, but Na plus Cl minus Na plus, you get the idea, Cl minus. And underneath it, I'm going to put a Cl minus and an Na plus. And I'm only going to do 3 lines of this. Plus Cl minus Na plus. and then Na plus Cl minus, Na plus Cl minus, okay? So even though within one of these units we can say that it's within intra, adjacent units are attracted to each other. So the Cl negative of one will be attracted to the Na plus of the other. And because the charges are full charges, positive 1, minus 1, these are very strong interactions. The bonds we say are directional. And I think I already showed you the Princess Tesa magnets once, right? And that's when I was showing you that model that I tried to make, and then I squished it, and I might be able to put it together here quickly again. But this can represent a tiny little ionic crystal. Again, the bonds are very directional, which means the structure is strong. The bonds are very strong. They're held together very strongly because the charges are complete positive and negative charges. So an ion-ion force found within an ionic compound, what physical state would you most likely find a substance that has these ion-ion forces? What physical state would you most likely find this particular substance? Peter?
In a solid state?
Solid, because they're strong, very strong forces holding them together, and they're very directional. So we've already seen that, ion-ion forces. All right. So now we're going to move our way down to slightly weaker forces. And the next one is called dipole-dipole. Now you'll notice the naming is not very creative. It means one ion is being attracted to one ion. And now we're talking about one dipole being attracted to another dipole. And we now know where dipoles come from. They come from unequal sharing within the bond due to a delta En. And once we have these dipoles, put a bunch of those molecules together, and you will have an interaction. Now, to represent that, I got a whole bunch of stuff in here. So polar molecules will be attracted to each other due to the partial charges. These forces are not as strong and not as directional. So to represent that, I just need a pile of magnets like this. Each one of these individual magnets is a dipole, because a magnet is an example of a magnetic dipole. This is an example of an electrostatic dipole, because it's electric charges. But the attractions are the same. If they're not very strong, then they will clump together, but they won't have a nice definite form. So right here, I'm representing a bunch of dipoles that are stuck together. If ion-ion is really kind of like, a nice directional strong solid, then, you could imagine I have this as a bunch of molecules, and I could stick it into a beaker like this, and notice how that group of molecules takes the shape of the container. I guess I could pour it. It doesn't pour very nicely, but you can imagine that I pour it. And you could imagine that it kind of spreads out a little bit on the tabletop, but not too far away. What physical state would this be most likely in? Yep. Yeah, this is behaving like a liquid. They're kind of clumping together, but they're clumping in a disorganized fashion, so they're not really kind of getting themselves organized in a nice solid state. So dipole-dipole tend to be liquids. Now, I'm giving you guys really just the basics of this idea. There are far more complex other issues that need to be discussed to determine exactly what type of state a substance is going to be in. But we're just giving you kind of like an introduction to this idea. We do it in more depth in grade 12, and then in university there's even more. Now, there is a special kind of dipole-dipole interaction, and it's really, really special. It gets its own name. You'll notice I haven't given it its own number because it is a special kind of dipole-dipole, and I just write dip-dip because I'm too lazy to type out dipole-dipole. So this is a special kind of dipole-dipole, and it's formed when hydrogen atoms bond to a certain group of atoms, and that group is stated. Nitrogen, oxygen, and fluorine, these guys here in the upper right-hand corner. Because of the high electronegativity of fluorine, oxygen, and nitrogen, when they form bonds, the dipole is really big because the separation of charge is quite big. The delta En is large, so the dipole is big, and that means that it's strong. So it's a special strong kind of dipole-dipole interaction. Now, this is not a bad little picture here to represent it. It's a little complicated. I might try to draw a simpler one on the board for you. But it's representing water molecules with the positive hydrogen end being attracted to the negative oxygen end. Actually, I'm going to draw a picture for you. I'll try to draw it on the slide here to represent that. So let's just simply draw a water molecule like this. Because of the lone pairs, it's not symmetrical. Again, I want people to kind of listen to this, so I'm going to take a look to see what the writing is happening. Everybody's still writing. I'll be patient here for a moment. So again, as I was stating, this picture here is a representation of a bunch of water molecules interacting with each other. And it's complex because there's lots of them. And it's true, that's the way they kind of behave. There's lots of ways for water to hydrogen bond with another water. But I'm only going to put 2 water molecules in my picture so that when you draw it, it's not as complex. But remember, in water, the oxygen has the high electronegativity. Remember, it's up near the top, the upper right-hand corner. If we check our chart, we'll see that it's a fairly high number. That means the oxygen is going to be a slightly negative end. And the hydrogens are going to be slightly positive ends. And again, a lot like the HCl, when you get a bunch of water together, that water will attract to a neighboring water, and I'll just draw a second one. Again, I'm going to put slightly negative, slightly positive, slightly positive. That's very important information for you to know, that in a water molecule, the hydrogens are the negative ends, and the hydrogens are the positive ends, and the oxygen is the negative end. And what can happen there then is that there can be that attraction for the other water molecule, and it is this attraction here that I'm going to label right there, that is the H bond, or hydrogen bond. Many students confuse it and they think it's the bond between the oxygen and the hydrogen in the water. No, that's a single covalent bond. It is the force of attraction between the oxygen of one water molecule and the hydrogen of another water molecule. That makes water a very sticky substance. Really what we're talking about is the stickiness of the molecules with respect to each other. When it comes to ionic compounds, they're really sticky. They stick together so tight that they make a strong solid. But when you're dealing with something like water, it's kind of sticky. It's not super sticky, but kind of sticky. But you've encountered that before. If you get water on your hand, right, it kind of drips off and you can see it's dripping, yet it's still hanging on to my finger. So there's a drip hanging on there. And the reason it's hanging on is because all of the water molecules in the drip are hanging on to each other. It's as if they're hanging over a cliff and they're saying, no, no, don't fall. And they're hanging on to each other in some kind of way to keep them from falling. If the drip gets too big, gravity takes over and it takes the drip away. But water is really quite a sticky substance, and it's because of its hydrogen bonding that does that. That's why, it takes a long time to dry. You also see that effect if you've ever taken juice or water and you fill a cup up and you're getting right close to the end of the liquid in the pitcher, right? But you know what teenagers do? They'll leave just that much, and then they'll put it back in the fridge, right? So that's what most teenagers do. But some of you might get brave and you might think, oh, I can do it. I'm going to make this fit in there, and you just keep pouring. And if you've ever done that, you might notice that you can actually pour it over the top of the glass. Have you ever noticed that before? Where you can pour it above the glass and you're down there and you're looking like, whoa, look at that, I filled it right up. Then you gotta slurp it up, because if you touch the side, it spills all over the place. The reason you can pour it over the top has everything to do with hydrogen bonding. So beverages are predominantly water with a little bit of sugar and various other sweeteners and things in it or whatever. So it's predominantly water. So what's happening is on that surface, just like the drip's hanging on, those water molecules are like holding hands going, whoa, we're going over the top, but I'm hanging on. I got a strong attraction for my neighbor, so I'm not going to go over the top and spill over the top, okay? Same thing if you spill some water on a desktop or on the tabletop, right? You get water on there, and you'll notice the water kind of piles up. You guys are pretty well at the level of the desk. If you bring yourself down to the desk, you can see there's a great big pile of water on the desk. It actually sticks up. Exactly for the same reason. The water is all kind of hanging on to each other, and it's not spreading out, really flat. Different liquids will. If you had gasoline and you spilt it on a desktop, it would go really flat and spread right out. If you did the same with something like acetone, which is found in nail polish remover, if you spill that, it gets really flat. It spreads out. That's because those molecules are not sticky. They're not hanging on to each other. Okay, so hydrogen bonding is a very special thing. All right, now for the last type of molecules that we haven't talked about, and those are the non-polar guys. We've talked about the ions, what do they do? We've talked about the polar ones. What about the regular molecules that are non-polar? What will they do? I am going to draw a little picture on that as well once you're done writing to kind of describe what's happening. And I know there's not a lot of room, but it can easily be done there. Now, this explanation is a very simplistic view of this idea of what we call London forces. Very, very simplified. In actual fact, as you continue on in chemistry, if you were to actually keep that note, you would find that it's really downright wrong. But it's a very simple way to introduce it, and I don't want to get it too complicated at this point. So non-polar molecules, they don't have any dipoles. So the delta En is so low or zero, and there is no charge that has been moved around. It's a neutral thing. It doesn't have a delta negative, a delta positive. However, there are very weak forces that exist between the adjacent molecules. We call them London forces, named after the scientist who kind of first proposed them and mathematically kind of calculated how strong these forces would be. There's another name for them, sometimes called van der Waals forces, and named after a Dutch scientist who also proposed a similar idea. They're also sometimes called dispersion forces, and I'm not quite sure why they use the term dispersion, because it's attractive. It doesn't really disperse anything. We're going to just call them London forces. The positive nucleus of one atom or molecule can attract the electrons of an adjacent atom or molecule. All right? This results in a weak attractive force between them, and the more electrons that an atom or molecule has, the stronger this force is. Now, there has to be something that happens to the atom or molecule before this force can be felt. And the atom or molecule has to be slightly deformed, as if it's being kind of pushed or bumped by another molecule. And so this little deformation is what needs to be initiated before these little attractions take place. And I'm not going to have you worry about this idea of a deformed atom or a deformed molecule. All I want you to realize is that when, and I'll just use my finger here, when we have the nucleus of one, and I'm putting a little plus in the middle there, and the electron orbit, right? And I'm going to put a little electron on the end there with a dot. So that's a nucleus, and that's an atom with it's an electron. And I'm going to draw another one beside it. There's a nucleus again. There's another orbit with an electron in it. Oh, that didn't work very well. I'll put that right there. And like I said, when they get close, they deform each other a little bit because the electrons are repelling each other, so it causes a little bend in the orbit. At that point, what happens is there's the ability to have this attraction between that electron and that nucleus, very tiny, weak attraction, and then another tiny, weak attraction back the other way. So there's this weak attraction between the electron from one and the nucleus from another. It's different than a bond because all the orbits are full. They've formed their compounds, but when they get close, they deform a little bit, and it causes this tiny little attraction. So it is very, very weak. In actual fact, it's so weak that under normal circumstances in a gas, the particles are so far apart, they're really not feeling that attractive force. The only time they can really feel that attractive force is if they get squeezed close together. Yep?
So are these like gases?
Yes, that's correct. So in my analogy here, right, I built the nice structure to represent the ionic solid, lots of directional bonds. Here, because these are all dipoles, they're representing a dipole-dipole interaction. And so now I need something that doesn't have any dipoles, and I'm going to analyze how well they stick together. So if I take a look at these marbles, which are not magnets, right? By the way, marbles are not magnets. They're made of glass. They're marble. And if I try to, have them, clump together, they don't interact with each other whatsoever. They don't clump together. So you put them out there in space, because there's no attractive forces or very weak attractive forces, they just go off and do their thing. And that's what gases do. They go off and they do their thing. And so they're not feeling attractive forces. So things that have only London forces are typically gases. By the way, one very important thing to have. All substances feel London forces. And I apologize writing on the screen. I'll just say it again. All substances feel London forces. Because all the substances that we've talked about, even the ion and even the dipoles, have electrons and have nuclei. So they will also feel London forces. The London forces just happen to be so weak that they're not even worth mentioning in an ionic compound. They're there, but the ion forces are so strong, they dominate, and it's not even worth mentioning, those London forces. But all substances feel London forces. Okay? All right. Let's now just do a quick little rank of the forces that we have talked about. And let's talk about what their physical properties will be. And what I mean is what physical state we'd likely find them in. So I'm going to just list my different intermolecular forces down here, right here, down the middle. And then we'll talk about what physical state they're going to be found. So, strong. What was my strongest intermolecular force that I have encountered or that I discussed with you today? What's the strongest? Peter, give it a break. What do we got? Rob, what do you got? Ion, ion. So, ion, ion. All right, that's a terrible N. I don't even know what that looks like, but that says, for those out in the world watching my video, that says ion, ion. I don't know what that is. Sorry, there's no video being recorded here. I mean, for those of you in my class that look at that letter and say, what is that? That's ion, ion. Let's work our way to, well, what physical state will we typically find ion, ion? What physical state will we typically find it? Solid. Solid. Next weakest, as we work our way from strong to weak, we're working our way down. Actually, we want the special one that's a little stronger. Josiah? H bonding, hydrogen bonding, an H bond, and then dip, 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 H bond and dip, dip. And when it comes to hydrogen bonding and dipole-dipole, the really weak ones, they tend to be gases. So hydrogen sulfide, well, actually, that's actually nonpolar. Hydrogen chloride, that HCl that I drew, that's a gas. That's typically found as a gas. But water, obviously, is found as a liquid. And so water is H bonding, and HCl is dipole-dipole. So in here, we're in between liquids and gases. But I'm going to just put here liquids, all right? So you could argue if it's dipole-dipole that it would be a liquid. But like I said, this is just a kind of an introduction. And now the weakest. The weakest of all of our intermolecular forces, Tim? London forces. London forces. And if it's not polar and there are no dipoles and the only force that's acting on those molecules, that's it. The physical state is, and I think we get the idea, they tend to be gases, all right? Something like carbon dioxide. Remember, we talked about carbon dioxide yesterday, where carbon dioxide is CO and O, and the two dipoles canceled each other out, right? We had a dipole that way and a dipole that way. Again, that makes it non-polar, and so that doesn't act like a magnet. It acts more like a stick, which they don't stick together in any way. So carbon dioxide is a gas, right? And the carbon dioxide is a gas at room temperature. Okay, so there's my lesson on intermolecular forces. And there is a few questions that deal with it. Now, I do have to finish off and talk about how we can distinguish between ionic and molecular forces in the laboratory. That was something that I typically do at the beginning of the unit, but we were running a little late on one of those. So I am going to finish off with a couple more little add-on notes that talks about how we distinguish between these things in a lab. And you can see I've got some equipment here, and hopefully I can show you a few things. Okay, so I am going to continue if that's all right. Actually, it doesn't matter whether it's all right or not. I'm still going to continue. Good to go? We got the homework written down? All right. So let's talk then, how do we distinguish between that? How do we distinguish between ionic and molecular? And you athletes can go. And I am recording this. Surprise, surprise. Of course. And the reason I was recording is because I don't have this on the video. And so this is what you're missing, and this is going to be on the video because I'm going to add it. You can go, don't bump my cart. Go out the back door. No. Yeah, no problem. Whoever you are. Unknown student.
Experiment
Unknown student number 1.
Volleyball. Thank you. See you guys.
All right. This is something that you probably did in grade 10, and that's great. I'm going to just quickly review it with you. And you probably did a lab on it, which is good. So we're going to use electrical conductivity to distinguish between ionic and molecular compounds. Electrical conductivity is the ability to allow electricity to run through it. And I actually really don't like that note there, because usually I like to kind of guide you into that thought process, but that's okay. It's good to write down. Because normally I ask them the question, all right, you've learned conductivity in grade 9 because you did electricity. And you would have been taught that you need to have this flowing in order to have electricity conducted. In grade 9. This little device here is a conductivity apparatus. I actually made these. It's pretty cool, eh? It's got a little resistor in it, and then it's got an LED at the top, and then it's got a 9-volt battery here. And if I touch these 2 electrodes at the very end to this tap right here, can you see that the LED turns on? Can you see it? That's fun. So there's a gap between these electrodes, and when I touch them to metal, it can then cause a complete circuit, and we then have conducting electricity. And like I said, in grade 9, you would learn about what needs to be moving or flowing in order to have electricity conducted. And if I don't ask Peter what the answer to this is, I think he's going to run out of the room because I've avoided him. So, oh, whoa, sure. All right, what do we got?
So on the note, it says that for electricity to be conducted, ions must be present. So does that mean that metals have ions in them? I thought they were
that's why I don't like this note. This note is designed specifically for when we study our ionic versus covalent compounds. That's why the question is asked. What were you taught in grade 9 that is needed to flow in order to have electricity conducted? And metals have lots of these. Electrons, right? That's what you're taught. And metals have lots of free electrons. And actually, we can explain that now. How strongly do metals hang on to their electrons? Not strongly, because they have a low ionization energy. That's why metals conduct, because those metal atoms are hanging around. They're all in a hunk of metal, let's say a hunk of even iron. It's got a fairly low ionization energy. So what happens is it looks at its neighbor and says, I got these extra electrons. I really don't care about them. Do you want yours? No, I don't want mine. All right. How about the neighbor down there? Do you want yours? No, I don't want mine. So if you put then electrical charges on the outside, the metal just says, here, take all our electrons. Just flow them along. Go ahead. Take them. Take them. We're going to give up all of our electrons because we don't care that much. So the electrons flow through the metal because they have a weak hold on them. Okay? So what then happens if we're talking about a solution or something that's dissolved? Now, I got to change the definition of what it means to conduct, because in grade 9, you're told electrons flow. But it's not the electrons that make the electricity flow. It's what the electrons carry. What do the electrons have as they flow? They have charges. They have negative charge. And so it's not electron flow that is conduction of electricity, but it's charge flow. There just has to be something with a charge moving along. Now, we know electrons have charge, but it turns out that ions have charge too. So let's take a look. If I then take my conductivity apparatus, and I've got 2 substances here, sodium chloride, which is ionic, metal, nonmetal, and then I have some sucrose, still in its package. I stole it from the coffee room. Don't tell anybody. So I took some sugar, which is molecular. It's got lots of bonds in it. And we want to take a look at how these things behave. So if I want to study whether it conducts, if I put it in the solid, you'll notice, does the light turn on? No. So there's no charges in here that are free to move. There's lots of charges in this substance. It's ionic. There's all kinds of Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus. You get it, right? See how I wrote that down over and over? But they can't move. Why can't these ions move? Yep. They're, pardon? No, that's not why they can't move. They've already done that. They've transferred their electrons. Why can't the charges or these things that carry the charges, these ions, Na plus, Cl minus, why can't they move? What do you think? They're stuck, they're locked in a cage of ion-ion bonds. They're stuck there. They can't move. We need to free them so that they can move freely. Okay, you're giggling because you feel I'm going to free ions, like out into the open. Let's free the ions. Okay, let's free the ions. How are we going to free the ions? Well, I'm going to add water, I'm going to dissolve it. Now, before I do that, I've got to do a little test. Here, I'm going to take some tap water, all right? And I'm going to clean off the end of this device. And I'm going to put this device in the tap water. And you'll notice what's happening here. Can you see it? You see it? See? What's happening?
The light is lit up quickly.
Thank you. It's conducting slightly. Tap water already has charges in it. It's already got ions in it. So if I want to do an experiment, I've got to use water that doesn't have ions in it. So I'm going to use some distilled water. I should be wearing goggles, so I just said this on the internet. Anyway, I am wearing goggles for safety. And I'm going to take some of this distilled water and I'm going to put it in this beaker. And I'm going to take the conductivity apparatus. And again, I'm going to clean off the end. And I'm going to put it into the distilled water. We getting any action there? No action. Okay. No ions in it. Perfect. So now we've got water that doesn't conduct. Let's take a little bit of the sodium chloride. And I'm going to swirl it around a little bit. I'm going to let it dissolve. And I'm going to set the ions free. I don't think I've ever said it that way. But now that Mackenzie's giggling, it is funny. Ions, I set you free. So what's happening when it dissolves? The ions are able to come out of their locked structure and are able to go into the water. Now they're free to move. They're floating around there in the water. Now I haven't dissolved it completely, but I don't need to. Again, I'll clean this tip off to make sure it's good and clean. I'm now going to put it in the distilled water with the ionic compound. And you can see there, it conducts like crazy. And so the reason it conducts like crazy is because we've set the ions free. The ions, we say, they're mobile. We've created mobile ions, moving ions. All right? So let's write down what happens in an ionic compound. And that little animation isn't going to work. So I'm going to just draw a picture. I'm going to hopefully draw a picture on here for you to put in here. I don't know if I can draw it in that container. I might be able to. Actually, I will. You could draw kind of an Erlenmeyer flask. What I'm going to draw down here is because we've dissolved it in the water, we have Na plus. Why is it disappearing? N. It's dissolving. Isn't that fun? Does the animation work? Nope. But I can't write on it. That's too bad. Look at that. It's dissolving. That's silliness. Is it? It probably is going behind the picture. I'm going to draw this on the board. So for those of you who are watching on the video, you're going to have to imagine what I'm drawing. I'm drawing a beaker. And then I'm putting water in that beaker. We're still writing that it conducts electricity? I guess so. Draw a beaker. Much easier to draw a beaker than Erlenmeyer flats. Look at, I can't even get the beaker straight. So in there, all I want you to draw is, well, actually, let's draw a little bit of Na plus, Cl minus, Na plus. There's my solid piece of salt that I put in the corner. And as it dissolves, it sends out an Na plus and a Cl minus and an Na plus and a Cl minus. And I'm just trying to draw them wherever. And I'm going to draw 2 electrodes going in. And I'm going to make one of them positive and one of them negative, which means it has a battery, but I'm not going to draw the battery in. And I'm going to draw a light bulb. That's a little filament of the light bulb with the bulb around it. And where is the Na plus going to head? This set free ion. Where's it going to go? Where's it going to go? Where's that Na plus going to go? Nope, not even going to share, not even going to participate. She's had enough of this. Yep. To the negative. So this guy's going to wander over here. And this guy's going to wander over here. And the Cl's are going to wander to the positive. So the Cl's are going to wander over there. The Cl's are going to wander over there. And this movement of charges means it conducts electricity. So we call them mobile ions. The ions are free to move when dissolved. They've been set free. All right? Now, if I do the same experiment now with some sugar, and sugar is molecular. It's made up of a bunch of carbons and hydrogens and oxygens, and they're in rings and all kinds of different things. So I'm going to take, again, a little bit of the distilled water. And I am going to test the water. The reason I have to test the water, even though I've tested it once, if I have a beaker that was dirty and had already an ionic substance on the surface of it, that might dissolve. It might affect the experiment. So let's test that water. And it's not conducting because I have a dishwasher and they get cleaned really well. And I'm going to take some of the sugar. We're going to add some sugar in there. That's enough of the sugar. And my garbage can isn't there. That's okay. And again, I'm going to swirl. And I'm not going to get it all to dissolve, but there is stuff dissolving in there. The salt did eventually all dissolve. The sugar would eventually all dissolve. But I think we've dissolved a fair bit. Let's now put it in again. And let's check the conductivity. And I'm in the liquid now. And you can see there that it doesn't conduct. And that's because there's no charges in the molecules. They're locked into the bonds. So ions cannot freely move. And so molecular compounds do not form mobile ions. Oh, I just dumped sugar all over my lab bench. Couple of terms that go along with that. The ionic compounds, they form what we call electrolytes. It means that they can conduct electricity. And molecular substances do not, and therefore form non-electrolytes. But there is an exception to that. Acids, which are molecules, do conduct. They actually behave a little like an ionic compound, so they are special. So acids are special. And we're going to talk a little bit about acids tomorrow. And if you can see the tiny little numbers on my slide, that says 12 of 13. So there's one more. And this last little thing that I want you to write down I've already shown you. I already gave you guys my Harry Potter show when we were talking about generating light. But now we know how to explain it. Actually, I'll show it to you again right now. It's not going to work that great again today because it's fairly humid. But if I take a substance like water and I bring a charged rod close to that substance, it's terrible. I've never had it work so poorly. Got to generate a charge here. There we go. That's fun. You ever seen that? You've seen that before. I've shown it to you, right? So if I bring a charged rod towards this polar liquid, I can get it to bend. And that's how we can distinguish between polar and non-polar liquids, right? If you had a liquid that was not polar, like bromine liquid, and I can't show you that because it's kind of a disgusting material, it wouldn't bend, but that bends. So what's happening in there? Well, oh, so much writing. That's what's happening. And I'll draw a little picture to illustrate it. And now my little numbers say 13 of 13. You'll notice on that left-hand side for polar liquids, it says I can use a negative or positively charged rod. If I rub this plastic rod up against the plastic bag, it generates a positive charge. Actually, it makes a much better positive charge. I can actually get the, I wonder if I can actually get the water to land into a beaker. Think I could fill a beaker from the side of the thing? Nope. I need a little more charge, I think. And I need a higher tap. Come on. Well, but then you can't see it. That's not nearly as exciting. I guess I could do this. Yeah, I'm touching it and then it changes. All right. Doesn't matter whether it's positive or negative. It'll work. I'm going to draw a little picture to represent it. So on this side, I'm going to just draw a circle, and I'll put a positive charge in the middle. That's like looking at the rod straight out at you. And I'm going to draw some water molecules falling here. So we're going to have the O and the H and the H and then an O. And what happens is, as it gets close, it will turn to have that negative O. Remember, the O is slightly negative, and it's going to bend around the corner, slightly negative, and keep bending around the corner, slightly negative. So what does that do? It makes the liquid kind of come down and bend around the corner. All right? So I've drawn it with the O's getting close to the plus, and it bends around the corner. If I use the other charged rod, the H's get close and bend around the corner. It makes no difference which charge I use. On the other side, to finish it, I'm going to, again, I'll put the plus, and then I could put like BR, 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 BR. There's no dipole, and so the bromine just falls right past that charged rod, doesn't bend, doesn't do anything. Okay? All right.